welcome to this talk about how to use application-layer encryption to prevent database breaches. My name is Philip, and what we'll be going through today is essentially a little bit about database breaches, some stats about why these types of attacks should be a concern to you. We'll talk a little bit about the traditional way of protecting databases, and highlight some of the shortcomings of those approaches. Then we'll talk about a newer, more, let's call it paranoid approach called zero trust architecture. And then we'll look at how application-layer encryption can help you implement such a architecture in your system. And then I'll finish off by talking a little bit about some advanced techniques that can help you make this application-layer encryption more usable. So database breaches, or indeed any type of data breach, are becoming a more and more prolific type of attack. Last year in 2021, we saw over 5,000 confirmed breaches. And these affected almost 300 million people. So they have a fairly large impact at this point. And an interesting thing here is that attackers are not only targeting small unprofessional businesses that have bad security, they're also targeting very large companies. So we had 43 quite high-profile cases last year involving very large companies like Facebook, LinkedIn, Microsoft, etc. And the reason why attackers target these high-profile companies is because they also stand to gain much more. Indeed, in these types of attacks, we often see millions of records leaked, which of course translates to a higher profit for the attacker. On the other side of that coin is the fact that an average data breach costs about, the company that gets hit has a cost of about $4 million as a consequence. So these types of attacks are getting more and more valuable for the attacker and more costly for the companies, and of course also impact people that have their personal data stolen. I think one of the big issues in trying to prevent these data leaks is that there are so many different attack vectors. So I've listed some of them here, and maybe at the top of the list is the human error thing. And this is where a configuration was bad, or someone accidentally exposed an endpoint that they shouldn't have. Basically stuff that could have been prevented, but because we're all human, we sometimes make mistakes. Another very common thing is that a database being protected by username and password, and then that password somehow gets leaked. This usually happens because database administrators, for example, have to access tons and tons of databases, and having to create credentials for these becomes quite a big chore. And the more credentials you have, the higher the risk there are of leaking them, because you might not handle them as well as you should have, because it's simply a hindrance to your daily work. Then from the stats here, 2019, we can see that maybe the most common cause is hacking. So this would be exploiting code vulnerabilities or 0 days or what have you to gain unlawful access to your data. Then there are the more human approaches, phishing and physical theft. So this would be trying to manipulate someone into giving you a password, or simply just stealing their laptop where the credentials for the database are. Finally, I want to mention inside attacks, because this is something that might not occur as often, but really has devastating consequences when it does. So this is typically a disgruntled employee who wants to make a quick buck before they exit the company, or just wants to destroy the company's data before leaving. So even though those attacks are not that common, they're really devastating to a company when they occur. One good example that is very relevant currently is this example of this log4shell exploit that we saw last year. So this was a critical Java vulnerability in a very commonly used logging library, and it was introduced, this bug, in 2013, but it wasn't discovered until 2021. And this is one of those really terrible exploits that basically give you direct access to the vulnerable machine in a remote code execution attack. All the attacker has to do is to get the target to log a specific string, and then they have access to the machine. So this would be a very strong, easy way of getting access to a database. And this can happen even though the Java application that is vulnerable does not necessarily talk to a database directly. It could happen by the attacker getting access to one part of your network and then laterally moving through your architecture until they find access to a database or credentials for a database. Now, of course, any good company with some good security practices don't just leave their databases open to the world. And we have traditionally had a number of ways of trying to protect our database from malicious access. And what we usually have here is a layered approach where at the outer layer we have network security. So this is stuff like firewall rules that prevent people, for example, outside of the network, from accessing your database directly. Then we have access management, which usually means creating users and passwords for your databases. And these are typically also tiered, such that some users have access to delete tables, for example, while others just have access to read. Then we have threat protection, which is typically monitoring of your system, for example, by deploying a SIEM. And this will allow you to sort of detect whether any malicious or weird-looking activity is happening in your network, and then try to stop it. And finally, we have information protection. So this is typically TLS for transport encryption over the network. And then we have encryption at rest for the data that is actually in the database while it's not being used. And while all of these measures are good to have, there are also some issues with them that do that they're not completely effective, right? So for network security, what we often see here is that an attacker will breach one area of your network, maybe completely disjoint from where your database is, and then they will move throughout the network in what we call lateral movement until they find a database. So the only way to sort of avoid this with network security is to completely lock down your network, right? For access management, this is also what I talked about before. We often see this problem of leaked or lost or stolen credentials for these databases. For monitoring, this is sort of obvious that the only thing you can do with monitoring is to detect that something weird is going on. You cannot actively prevent it. What you do gain, of course, is then some alerting, and then you can try to stop an adversary. But this also means that the adversary will always have some time to do damage. Finally, for TLS and encryption at rest, the problem here is that this is very ineffective against legitimate looking access. So if someone gains access to, for example, a backend application that has access to your database, well, that backend application needs to be able to read the data in the database, and so your encryption at rest doesn't really help you there. Alright, so what can we actually do to improve the situation? What we can look at is this more modern tool of how to think security named Zero Trust Architecture. And the whole point of this setup is to basically be as paranoid as possible. So I think a way to summarize this way of thinking is never trust, always verify. And there are sort of three core tenets in Zero Trust Architecture. The first one being verify explicitly. So this means that whenever someone is trying to access your network, for example, then you should authenticate them and you should authorize them based on all the available data points that you have. So this means who are they, what are they trying to access, when are they trying to access it, what are they trying to do with the data, etc. And I think the important part to highlight here is the authorized part. And this brings us to the next point, which is about least privilege access. So you should try to limit the access to your architecture to giving an entity just enough access to do the thing they need to do. So this could, for example, be if a user only needs to read data, then they should only have access to read data and not to write it, for example. And finally, the last pillar here is to assume a breach. And what this means is that you should assume that all access could be malicious. So any point where anyone is trying to do anything, you should think, okay, what would happen if this was actually a malicious actor trying to do something bad? What can we do to then minimize the blast radius of such an incident? And the thing you have to think about here is that these three things have to happen at every point in your architecture. It's not only on ingress into your network, for example, but also traffic inside your network. These rules also apply. So really any component of your architecture should think of any other component as potentially malicious, right? And what you gain by implementing this zero trust architecture is several things, right? First of all, it forces you to think security. When you have to uphold these three tenets, you have to always think what could go wrong if someone was trying to do something bad. So that gives you a very strong foundation of security in your architecture. Another benefit you gain is that all traffic, not just traffic that is leaving your system, but also stuff that is inside your perimeter, is secured. So even if an attacker would somehow get some visibility into the traffic in what you would normally think of as a secure location, they don't really gain anything. You also gain increased visibility because at any point in time and in all components of your system, you have to authenticate and authorize the access. That means that you can also track all the access. And you can also very explicitly see what people were authorized to do. It also somehow somewhat minimizes the impact of an insider attack, because even insiders should be treated as potentially malicious players in this setting. What you also gain, which is really nice, is that attackers that somehow do get access to your system have very hindered lateral movement, so they cannot necessarily easily jump from one system to another because they have to be authenticated and authorized inside your system as well. And then the possibility of data exfiltration is quite limited as well, because you should only give an actor inside your system access to what they need, and an attacker can maybe only spoof, say, access to read data for one particular user, and then they can only exfiltrate that part, so they won't get access to the entire database, say. So now the question is, how can we actually realize a zero-trust architecture around databases? And one tool to take quite far in this approach, in this endeavor, is to use application-layer encryption. So what does this actually mean? Well, let's look at this very common setup where you have an application, and that application needs to have access to a database. What a lot of people then do is that they provision a database with some cloud provider, and typically when you do that, there will be some VM in front of the actual storage of the database to manage sort of the access to that database. And how do you then secure this setup normally? Well, what you would do is to use TLS for transport encryption, so the actual connection between the application and this VM. And then you would use encryption at rest at the VM to store encrypted data in the database when the database is not in use. And the problem here is that you encrypt data at the application, and then it is decrypted at the VM, and then the VM re-encrypts it and stores it in the database. So the first problem here is that the data is in plain text in the VM. So the VM here becomes a weak point in your security. If someone gains access to the VM, they can see basically all the data that's flowing through it, and the VM will also have access to all the data in the database. So encryption keys are exposed to the cloud vendor because they are the ones doing the encryption. Even if you're using a bring your own key scheme, then because the cloud provider in this case is the one doing the at-rest encryption, they also need to know the encryption keys. So an operator here could access your data at any point in time, or someone who gets access to the operator could access your data at any point in time. Now instead, what you can do is to use application-layer encryption, and this means that instead of doing these two-step sort of encryption, you have the application handle the encryption logic. So the result here is that the data that flows through the VM is completely opaque to the VM. It has no way of decrypting that, and the cloud provider furthermore has no way of accessing your data. So that means that as soon as sensitive data leaves your application, it will do so in an encrypted form. So I think what's important to highlight here is that when you do application layer encryption like this, you should think about encrypting data as soon as possible. So as soon as you, for example, generated some data and you no longer need to operate on it, then encrypt it. And the same the other way around. You should try to decrypt as late as possible. So keep data in its encrypted form until you need it, need to actually see what it contains. Then you can decrypt it and use it. That is the first part here. The second part, I think, which might be often overlooked, is that you should authorize access to data at the encryption layer. So the logic for making decisions about who can actually access this data should be at the encryption layer. What you gain here is then, or what you can do is have very fine-grained access to data, so that only entities that absolutely need access to this data can decrypt. And you can also scope access to required operations. For example, some entities might only need to be able to read data, some might only need to be able to write data. If you don't need both, then you shouldn't have both. And what I might be hinting at here as well is also that users should be defining the access, not the application. So if you have some front end that accesses stuff on behalf of a user, then it should be the user that defines what they have access to. It should not be the application. One way to do this is to connect this authorization layer you have in your encryption logic to your organization's IAM, for example, so that the encryption layer knows, okay, this user needs, at this time, they need read access to this specific piece of encrypted data, then I will decrypt it for them. So let's look at how this could look in practice. So here we have a setup that is pretty common. We have down at the bottom left, we have some thing that produces data. This could be, I don't know, IoT devices or anything else really, but they produce data and they send it to the cloud to some workload. And that workload somehow processes the data, maybe aggregates it, does some statistics on it, and spits out some sort of report, let's say, which is stored in the database. And then at a later point, the user on the top left would like to look at this report, right? So they access a web backend through a browser, for example, and that backend then authenticates them through an IAM and pulls out the data from the database and presents it to the user. So this is basically the setup we had before, where we have transport layer encryption here in green on the traffic to the cloud environment, and then the database itself uses encryption at rest. Again, here we have the problem of if someone gains access to the web backend directly, then they can of course access the data, and same for the workload. So how do we apply application layer encryption here? Well, we need to bake in the encryption and authorization logic into this workload and the backend. What I've also illustrated here is that we can then put the database in whatever other environment we would like, because the database no longer contains any sensitive data. So what would this actually look like in practice is that as soon as the workload receives the data and has processed it, it encrypts it. And remember that authorization for what this workload is allowed to do should be in the encryption layer. So in this case, since the workload only needs to store data, then the encryption layer should only function one way for the workload, basically. So the workload is authorized to encrypt data and store it in the database, but if the workload tries to decrypt anything, the encryption layer will deny it the access. And this really helps with attacks where someone would gain access to the workload and then try to exfiltrate data from the database, because all they can do in this case is then get encrypted data, but there's no way for them to get the proper authorization to actually decrypt it. In the same way, the web backend should only have authorization to read, and more importantly, it should use the user's IAM authentication as information on how it is allowed to decrypt. So if the user only should be allowed to access a certain piece of data, then that is all the encryption layer should allow them to decrypt. Again, if someone then gets access to the web backend, they would also need to compromise the access of a user, and even in that case, they would only be able to decrypt data that user is authorized for. So this really helps with this zero trust thinking that we saw before, where the encryption layer really becomes the point where you can control with very strong guarantees who has access to what and when. So just to reiterate, the benefit you get here is that data producers have no way of reading data. So if an entity is there to produce and store data, there's no reason for it to be able to decrypt it. You can also limit data access at the field level. So typically, if you have traditional encryption at rest, then you just encrypt the entire database when it's not in use. But here you can say each field is encrypted differently with different access mechanisms. So you can really control, okay, a user is only allowed to access their own data, for example, and no other user is authorized to do that. Of course, what you then get here is that the entire database itself could be compromised without data loss. So in an extreme case, you could even put this database publicly visible on the internet for anyone to see, because there is no sensitive data in there. Only the applications have direct access to decrypt the data. And another strong point here is that data only appears in plain text when it's actually in use. So actually, when a user requests their data, for example, that is the only time when it will appear as plain text. So while this application layer encryption techniques give you a very nice approach to zero trust architecture, you also risk losing some benefits of a classical database if you just naively encrypt all your data. For example, you can no longer do normal SQL style lookups on your data. And you can alleviate this by using a number of more advanced techniques. So the first one I'll mention here is authenticated encryption with associated data. And this is a technique where you can attach plain text metadata to your sensitive data in such a way that those two cannot be separated, and the plain text metadata is still authenticated. So you can be sure that no one messed with that part of the data. This can allow you to do many interesting things. For example, put metadata on your encrypted data that allows you to do at least some type of queries. So this is one way of getting more visibility into your sensitive data without actually leaking important things. A more advanced way of doing this is by using searchable encryption. So this is a type of encryption where you can define keywords on encrypted values in such a way that you can then look up, okay, what encrypted fields, for example, contain a certain name or something like that. And the nice thing about this technique is that it does not reveal to any adversaries how many keywords, for example, there are, what the keywords are, in what documents they're contained, etc. So this is a slightly more advanced way of getting a very secure search on your data. Of course, this also comes at somewhat of a performance hit. Then you can also do this nice thing of using public key cryptography to very strongly tie your users to their data in such a way that you can cryptographically guarantee that only the user associated with a specific public key, private key pair can actually decrypt their data. In that way, not even the application can sort of spoof who the user is. The downside of this approach, of course, is that you have to put some trust in the users to manage their key material. And finally, the last thing I'll mention is a technique called attribute-based encryption, which allows you to have very cryptographically strong authorization on your data. Basically, whenever you encrypt something, you also associate attributes to that encryption. For example, only administrators are allowed to decrypt. And then you can cryptographically guarantee that only people who can prove that they're part of the administrator group can access this data. Alright, so that was what I had to share with you about application layer encryption. So I hope this inspires you to look into how you can incorporate application layer encryption in your architecture and hopefully move towards zero trust architecture with this tool and prevent your data from being breached. Thank you.